Okay, good morning, everyone. Welcome to this webinar organized by IABSE Italy and IABSE Germany national groups. This is the first appointment of two webinars dedicated to the Carola bridge collapse. And I'm Francesco Lomurno, structural engineer of Tecne SPA, an engineering company in Milan, and together with Giovanni, we will have the pleasure of moderating this meeting. I introduce Nadia Zoratto, that briefly will present the Italian group. Okay, please.
Thank you. Good afternoon and welcome to everyone. I will share a few slides to present also IABSE activity. Just a moment. Okay, before starting, only a couple of information for our attendees. First of all, the webinar will be recorded and then posted in the learning web page of IABSE. Second, you can obviously submit questions during also the presentation using the Q&A button. But obviously we will have the discussion at the end of both presentations. As anticipated by Francesco, this webinar has been jointly organized with Italian and Germany groups and is focused on the Carola bridge collapse and the causes that led to this event. Two words to remind you who IABSE is and what it does. IABSE is an engineering association with the mission to exchange knowledge and advance the practice of structural engineering worldwide, looking at all the aspects in structural engineering and all type of structures, not only bridges, and also to all the aspects related to the construction process. I remind you that you can become members of this great organization as individual and in alternative collective members. We have members in more than 100 countries. And for this reason, we have many national groups that are very active to organize events such as webinars and conferences. In Italy, we have also a national group that has been refounded recently in 2022. And we are trying to promote several activities with technical task groups and with dissemination and training activities such as webinars and short courses. Upcoming conferences, we will have the next IABSE Congress in Incheon, Korea, for mid of September. Consider that the early bird registration get over by June 30. Then, looking at the next year, we will have, as usual, a IABSE symposium on spring in Guayati. The abstract submission are going to close by the end of this month. And then we are proud to announce that the next IABSE Congress held in Italy, Milano, hosted by the University Politecnico of Milano. And the call for abstract is already open and will end by mid of September. We have several general and special sessions, so I'm sure that you can find a proper topic to submit your abstract. Webinars, I remember you that are free for all, even if you are not yet a member of IABSE. On the bottom side, you can see the link to see the past webinars. I would remind you that the second part of this webinar is planned for the next week, July 3rd. And I would bring to your attention also to another interesting webinar related to seismic response control, organized by Japanese and Philippines national groups and planned for July 6th. Now, I'm pleased, honored to introduce on behalf of Professor Siebert, the secretary of the German group, Mr. Seitz. Please,
yes,
the floor is yours.
Thank you, Nadia, for the kind words. A very warm good afternoon to all participants. As you told, I'm the secretary of the German group. Our chair, Professor Siebert, unfortunately is in a faculty meeting and cannot attend. So I'm very happy that the Italian group organized this event together with us on this very interesting topic. And currently we have about 70 participants online. I hope you can learn a lot of these issues for your future professional career, and I'm very keen on listening to the experts we have now. So I give the words to Giovanni for the next presenting the presenters. Thank you.
Thank you, Peter. Good morning, everyone. My name is G.Fanigliulo from Studio di Ingegneria delle Strutture, and I'm the Young Engineers Program Chair for the Italian National Group and YC board member. So I'll briefly introduce today's program. We have the first technical presentation, which is technical analysis of the Carolabrücke bridge collapse by Professor Gregor Schacht from the Dresden University of Technology and MKP, the Marx Krontal partner. And this will be followed by a presentation, Corrosion Mechanisms and New Findings, presented by Dr. Gino Ebell from the Federal Institute for Materials Research and Testing, focusing on the corrosion mechanisms and the latest findings from the investigations. I remind to everyone that at the end of the presentations, we will have a discussion and a brief Q&A session. So, Professor Schacht, the floor is yours.
Giovanni, thank you very much. First of all, I have to correct. I'm not professor. I'm just a managing director of MKP. That's fine. I'm not from the Technical University. Okay, but I'm glad. Yeah. Hello, everyone. I'm looking forward to present to you the findings of the investigations we have done to the collapse of the Carolabrücke in Dresden, and I want to start with the picture we have seen at September 11th in 2024. It has already 2 years ago almost, and there was a tragic moment when we started to see this collapsed bridge laying in the river of the Elbe, and we have gotten the contract from the city of Dresden to investigate the result or the reasons for the collapse, and therefore we were at the site very early in the morning and started the investigations immediately in the morning when we could get on the bridge. And first of all, I want to explain the bridge or tell you something about the bridge. There are 4 parts of the bridge. We call the Altstädter cantilever and the suspended girder in the middle of the bridge, and the Neustädter cantilever on the other side of the bridge or of the river, and then just a single span suspended girder on the other side, on the Neustädter side of the river. And we have a typical cross-section, or the Carola bridge had a typical cross-section for prestressed concrete bridge. And what we see is in the section, or on the cross-section and the XSD, there was a lot of pre-stressing tendons in there, 194 pre-stressing tendons, and therefore the compression zone was also very compact and very strongly reinforced with a lot of reinforcement there, and a thick slab at the bottom. Yeah, the bridge was constructed in different phases. They started to construct the first part on the left side with the cantilever into the river, and on the other side, the second part with the bigger cantilever of 44 meters into the River Elbe to allow the ships crossing the side during construction. And afterwards, they placed the suspended girder in the middle of the river, and then they finished the bridge. Therefore, they had to pre-stress a lot of tendons afterwards, after the self-weight of the girder was active. And these tendons, and that is probably one of the main reasons, many of these tendons were already placed in the tubes or in the concrete, but not pre-stressed. Some were pre-stressed but not grouted. So there are a lot of pre-stressing tendons laying there for a long time in this construction. They took a lot of care in the construction itself. They placed heated barracks to prepare the tendons before placing them into the cross section, and they were aware of the danger of this pre-stressing tendons to fail brittle, so they put a lot of efforts in preventing this to happen. There was one specific construction detail I want to focus you on, this cross girder between the superstructures. They connected the superstructures at the tip of the cantilever, and that was done because they wanted to assure that all three superstructures have the same height. So they forced them together and arranged the position of the superstructures to each other to align them on one height. And this cross girder was one of the main reasons why the collapse took place 8 minutes after the last tram crossed the bridge, and not at the moment where the load was on the structure itself. Yes, to have a side view on the collapsed bridge, we have the XSD on the left side, where the breakage started. We have the cantilever, the 44-meter cantilever on the one side, the suspended girder, and the other hinge here remained on the cantilever of the Altstädter side. Yes, and at the beginning it was not clear where the breakage started, and you see here at the XSD the opened cross section, and here is the cross girder I was talking about, placed at the tip of the cantilever, and therefore the three superstructures were connected at that point to each other. So they carried the load with each other and shared the load with each other. At the beginning, as I said, it was unclear where the breakage or the collapse started, and therefore we were happy to have a video from the ships placed at the River Elbe. They were actually trying to film vandalism, and for us it was a happy reason they filmed the collapse itself. And when we focus maybe on this white car you see on the bridge on the right side, I hope you can see my mouse, and I will just start to click the single pictures, and the car is moving with around 50 kilometers per hour. And you can see at the next points, you maybe focus on the lights of the bridge or at the top, and you will see the beginning deformation of the bridge. Now you can already see that the deformation is starting. I hope the internet connection is good enough. And as the car goes further, you now see already the bridge is moving downwards, and then it goes really quick. We were able to see the opening of the cross section at the XSD in this video, and therewith we could explain how the collapse started and where the failure started to progress. Yes, now the self-weight is active and it's only falling into the river. There's now lightning coming up from the electrical power of the tram, and then it was over. Oh, I'm sorry. Yes, that's the last picture from the ship of the collapse. And at the morning, at the side, it looked like that. We see the cross section at the XSD on this side cut, or it looks like it was cut with a knife and opened up. Yeah, only at one cross section. And at the beginning, it was not clear whether what kind of damage we have here. We see all the tendons placed in the on this side and the slab at the top here and on the other side. And what we can see already is that the broken wires of the broken strands are broken at different points. They are looking like spaghettis. When we break spaghetti bundle, it looks like these tendons look like. Many of the breaking points were inside the tendons in the cross section and some were outside. So that was what we saw at the first day. And as closer we could get, and we started to documentate all tendons with a drone to film all the tendons and to make pictures of them. And then we were getting closer and closer. And what we found was also, maybe one example is this tendon or this wire here, broken at two sides, which is untypically for a prestressed tendon to fail on two sides, on two breaking points. Yes. And as closer as we came to the tendons itself, we saw different corrosion states of the tendons. We had already brown tendon or breakage points, cross sections, which were brown and totally corroded. Gino will explain it later on. And we've also found wires that failed ductile, which had typical uncracked, starting cracked or cracked stress corrosion cracking, these little lenses which form into the steel, which is typically, we can also see it on these tendons up here or these wires up here. And we had, as I said, different states of corrosion with a lot of brittle failed or brittle broken wires in these tendons. That was pretty clear at the beginning. And after we evaluated the pictures of the camera, we were able to cluster the pictures we were able to detect with different cross sections which were remaining at the time of the failure, and we were able to localize them with the pictures. And as you see, many of the wires in the slab of the Carola bridge have been already broken, and there was not even any or only a few wires left in the tendons which were active at the moment of failure. And in these areas we have yellow or green tendons which were sometimes totally working, totally correct, and some were already damaged totally. So at the beginning, and I just go back to more pictures, at the beginning it was not clear what was the reason for this corrosion, and we had many different suspects. We had maybe chlorides coming into the isolation of this superstructure, because we have all this tendons broken at the top here at the slab. Maybe this electrical element here was one reason. So there were a lot of things we were trying to find out which we could exclude from the reasons, and therewith we got closer to the one reason we had for the Carola bridge. And Gino Ebell sent this picture to me around Halloween, and at the beginning, at the first time I saw it, I thought it was an artificial intelligent constructed picture, because the many cracks we have seen on the wires were new for us at that moment, because we have never seen wires that had that many cracks already inside. So all these little green lines you can see on the one wire you see here are already cracks of the material itself. Yeah. And we did a lot of tests at the superstructure C, which was falling down. We had to hurry a little bit because, as you can imagine, there were a lot of people there, the police, the fire workers, the army was there, a lot of people who wanted to really quickly demolish the bridge, and we were there to find out what happened. And that was not always easy when the machines are working and demolishing the bridge, and you try to collect as many tendons as you can. But what we found was also tendons which had mortar, grouting mortar at the cross section that were broken, and that was therefore a proof for us that the wires were already broken at the moment the grouting was done in the past. Yes. And at the bridge, there was 29 of 53 samples we took were already cracked. And we did the same investigations at the other two superstructures, A and B, and at the superstructure C only at some spots because the bridge was laying in the river, had to be demolished because of the high water coming up at the time. So we had to the chance to test a lot in this superstructure C, but we did a lot of testing in the other two superstructures, A and B, and what we found out is that
Gregor, I think you are having some connection problem.
In the regions of the supports, always at the top of the bridges, of the cross sections of the fields, we didn't find. That was the finding January, March, maybe March 25, and been investigated in Germany. Saxony, the federal state of directly. We had the bridges in Böen, a lot of pre-stressing wires that were cracked.
Gregor, we don't hear you anymore.
Okay.
Your internet connection is
better now?
bad.
Okay. Yes, now it's better.
Now it's better.
Not much.
Yes, I think we lost last minute. If you can check your connection and repeat your last minute of presentation. I think your connection is bad
I will
now.
Continue. Okay. Francesco, can you hear me? Or Giovanni?
Yes, now I think it's better.
Okay, then I can continue.
Yes.
I already said that that we investigate. What you can see here is the areas where we found broken wires or cracked wires, which are already the red lines, and in the cracked wires. So what we concluded was that we find something what was till then unknown, that a lot of wires are cracked above the supports. And after the collapse of the Carolabrücke, the federal state of Saxony began to investigate other bridges, and and many of them are already demolished, others are monitored or will be renewed with new bridges, and a lot of bridges are closed already in Germany because they have the same damages caused by stress corrosion cracking, as Gino will explain to us later. And this is right now, and therefore we don't know if it is only a problem of East Germany or for all pre-stressing wise. But Gino will go focus that. I will skip this, or I just want to quickly go on this phenomenon. The stress corrosion cracking is initiated in the phases of construction till the pre-stressing tendons are grouted, and afterwards the cracking will not continue to grow from the chemical point of view, but will continue to grow through fatigue stresses, which will make the crack grow deeper into the material till the wires break. Yes, so we have a new phenomenon which is showing that cracks are not equally distributed along the longitudinal axis of the bridges as we have supposed till 2 years ago, maybe, and which is the basis for all our analytical evaluations. But we see that cracks are localizing above the supports, and that are also the points, also the corrosion is starting initiated at these points and processes in these areas quicker than in the other areas. So the main finding is that we have to look on the high points of the tendons to determine whether we have evaluated the investigations of 27 bridges, and we found and have tried to evaluate where, at which places of the bridge or at which areas of the tendon in longitudinal direction we found stress corrosion cracks and where not. And we found that with a probability of 93%, you will find stress corrosion cracks in all these bridges in the top points of the tendons and only in the low points only with a probability of 30%. So the main point where we have to look at this bridge or not is to look into the high points, and that is what we right now have not done in Germany. That's why we will change our testing routines, our inspection methods to determine whether the structures are affected with stress corrosion cracking or it is not. Because right now we have always looked in the low points of the tendons and mainly did not find anything. But this is a new thing we found out at the Carola bridge. Yes, I've just put some remarks on the slide here. The main fact is that the condensation of water during the state of construction, connection with sulfur dioxide, Gino will explain that in the next presentation, is starting, and then the brittle steels crack during or by fatigue in the time during usage of the bridge. We are not sure whether we have a prior announcement of the failure at the Carola bridge. This the proof we are calculating for a prior announcement of failure was satisfied with a high safety level at the XSD, but it did not show up, and we had only very, very small cracking in the support region, and these cracks were not seen or detected at failure of the upcoming failure. So we have to look more closely to cracks in this points, especially in the high points of the tendons. What we also will do is that the Federal Department of Transport will give a new guideline to the engineers to evaluate the new findings, or to all the bridges with the new findings, and this will change the doing and the rules we have right now. So this is in preparation and will be used in the next year. It will has 4 parts where the corrosion mechanisms are explained. The findings of the Carolabrücke are already also written down, and the individual points what the engineers have to do are written down in part A and explained in part B. There will be a prioritization of the structures, which have to be checked again, which have to be checked more closely, and to find out which structures are more endangered than others. We have to look for structural capacity, and especially bridges with high fatigue bridges with a direct connection of rails to the higher impacts, which cause a crack or cracking or breaking of the wires. Yes, as I said, longitudinal cracks with a small width. We have new rules for the assessment of these structures, and we will use a lot of, or allow a lot of new techniques as acoustic emission monitoring or fiber optical monitoring to evaluate the condition of the structures. Yes, and we haven't done a lot of research, or has been done a lot of research on this topic, but all the data that we have collected in the last 20 years was not brought together and analyzed sufficiently. So this will be done now at the Federal Institute of Materials. Gino Ebell will collect all the data we are getting from bridges that are demolished right now, and we will find out which steels are affected, which are not, and so we are able to, evaluate the danger of stress corrosion cracking better. Yes. Okay. I'm at the end of my, will continue.
Thank you, Schacht. We will now move on to very swiftly and quite in time to Dr. Ebell's presentation on corrosion mechanisms and new findings. So, Dr. Ebell, the floor is yours.
Thank you. I will share my presentation. So I hope you will see my presentation.
Yes, you can see it.
Yeah, welcome to my presentation about the corrosion mechanism and new findings of the collapse of the Carola bridge. First time I joined the collapsed bridge was several days later, especially 9 days after the bridge collapsed. And as you can see, the pictures regarding to the one you saw before of the broken wires inside are completely different. As I stay on the bridge, I just saw red rusted pre-stressing steels, also ducts, and the normal reinforcement is also completely corroded. So I could not differentiate between the cross-section loss due to the pictures you saw before. But in general, you will see that the broken wires don't have any ductile transformation during the collapse. So it could be a problem of hydrogen embrittlement, means brittle broken tensions. And the reason for that could be stress corrosion cracking. In general, we need 3 different ingredients. Susceptible material, means pre-stressing steel with a high strength class, an electrolyte and mechanical stress. If those 3 ingredients come together, we will generate a triangle where hydrogen-induced stress corrosion cracking could be possible. We already know that the Hennigsdorfer pre-stressing steel is high susceptible against hydrogen-induced stress corrosion cracking. Mechanical stresses are completely clear. They are always given in pre-stressing structures, but the electrolyte is not clear. How could it be possible that we have electrochemical reactions directly above the pillar on the highest point where no rainwater could take place, nothing else, And as you already saw, the ducts from outside are completely free of corrosion products. I'm not sure if you are familiar with electrochemical reactions, but in general, we need two different partial reactions. The first time is the anionic reaction, where iron went into solution, electrons are getting free, and it is necessary that those free electrons are consumed by the cathodic partial reaction. And therefore, it is possible by the Volmer reaction that we will get aqueous hydrogen inside of the electrolyte. This hydrogen atoms could be absorbed at the surface of the steel and could be absorbed by high equivalent hydrogen pressure into the steel. As you could see here on top, it is necessary that we will have a pH value lower than 5. Otherwise, the cathodic partial reaction reacts by reduction of oxygen and no hydrogen will be produced. So right now you will already have a question, how could it be possible that we will have a pH value lower than 5 in concrete structures? At the end of the building or of the structure phase themselves, it is impossible, because the mortar which fulfilled the ducts is always high alkaline with pH values higher than 12 or up to 13.5. These both reactions are not so necessary for us. This is also a picture which Gregor already showed. The cross-section of the girder right above the pillar at point D, and we will have a detailed look to these embedded tensions here. The anchors taking place inside of the box girder, so they are protected against rainwater. It is impossible that rainwater could flow into those dots. That's fine. And until they are completely, or until they could completely pre-stress the embedded pre-stressing wires, the end of the anchors is completely open. There are holes inside to press in the mortar and also to get out the air inside the duct during the fulfilling of the ducts themselves. But we will have a problem due to those big concrete structures due to hydration heat of the hardening process of the concrete themselves. So the temperature inside of those box girders is, maybe if you have winter time outside, it takes several weeks up to months until it is cold here inside. So it could be possible that we will have a temperature shift from inside to outside. Inside of the structure, maybe it could be possible that we will have 15 degrees plus with a high humidity inside. That's also clear inside of a concrete structure without any formwork inside. So hydrogen could diffuse into the box girder. And at the outside, during the winter time, you already saw the picture from the building process in the winter with snow on top. It could be possible that we have -5 degrees. So right now we will have a problem inside of the non-fulfilled ducts. Due to the dew point undershoot, which is only 0.8 degrees, it could be possible that we will get condensation water inside the ducts with forming drops on top at the inner side, but on top of the duct at the, I call it 12 o'clock position here at the upper side of the ducts. And now we will have a moisture content inside the ducts, which also could form moisture films on top of the embedded non-protected pre-stressing steels. But then we need to ask several questions. Could condensation cause such significant, or condensation water cause such significant hydrogen loading or evaluation alone? Is a pH value low enough to ensure a cathodic partial reaction with hydrogen evolution? That means the pH value of the moisture film needs to be lower than 5. Could there be other environmental influences, maybe air pollution, that interact with the condensation and drastically increase the corrosiveness of the electrolyte? And the harmful gases or the air pollution at the date of the construction starts, means in the late 60s of the last century, we have high sulfur dioxide contents of the air. And in general, in the former German Democratic Republic, environmental data was kept under lock. That's is top secret. But right now the values available, because they start to measure those air pollution values since the middle of the 60s from the last century. And here you can see some measurement points from Germany we already investigated. And these are the values from 1969. And here you can see during the heat period where everybody is used coal to produce more or less heat inside their flats, and they also used it to produce electricity without any sulfur filters inside of the power plants. That means we have highest values up to 1,050 micrograms per cubic meter of sulfur dioxide in the air. Comparing for you, right now, current measurements at a highway during the winter time, we have 1.04 micrograms of sulfur dioxide in the air at the same time. So there is a gap of more or less 3 decades. So, but we are able to produce artificial environmental conditions in a special chamber. It's called a Kestanich chamber, and there we filled in 500 micrograms per cubic meter of sulfur dioxide. With these artificial situation, we used also artificial rainwater, and comparing the sulfur dioxide inside, we formed electrolyte film with a pH value of 3.55 after 24 hours of exposure. That means in a time span of 24 hours, we can shift the pH value just due to the sulfur dioxide content in the air from 5.8 to 3.55. Okay. With this result, we produced artificial moisture or artificial rainwater added with sulfuric acid to ensure that we will have a pH value of 3.55. Sulfuric acid, because the final reaction product of the reaction between sulfur dioxide and moisture films is sulfuric acid. It takes a couple of time, but afterwards it will be fine. And then we use the so-called Devanatan measurement cell. Here we can check the hydrogen evolution and also the hydrogen diffusion between the loading area and the verification area. Between those both areas is iron fold, the thickness of 0.05 millimeters, means 15 microns. And here we can fill in the artificial moisture film we produced in the chamber, or the artificial one we produced afterwards with the sulfuric acid. And at the other side, we can directly reduce the protons on that side by electrochemical measurements. And we directly get an idea about the volume of hydrogen which could diffuse through the iron foil. So now I will show you the first result where we used the artificial rainwater added with sulfuric acid. And the red line is the electrochemical potential at this stage, and pH value minus 600 millivolts is a clear corroding metallic surface or iron surface inside of this solution. And at the other hand, you will see the hydrogen transient during the measurement time, and it's about 0. And this is a result in case of signs which we don't want to see, but this is a kind of investigation, and this could always be could always happen if you have a great idea and it doesn't fit really. So, but the main reason why we have those high hydrogen evolution must be directly affected by the sulfur dioxide. So we thought about it, and between the exposure of moisture films and sulfur dioxide and the formation of sulfuric acid, there's a step between, and this is a formation of sulfurous acid. That's something different because we have a change in the anion. Here, as you can see, this is the last oxidation step of sulfur, and there's something between. The step before is SO3 2-. And you also, it's only one way to produce it directly in the chamber. It's no chance to produce it in an artificial way because the sulfurous acid is thermodynamically not stable. It directly oxidates to sulfuric acid, but the oxidation step themselves produces hydrogen at the steel surface. And this is what we investigated in the Devanatan cell, as I showed you before. The hydrogen transient, if we use the directly exposed moisture to the sulfur dioxide, could show those kinds of hydrogen transients here, up to 100%, with a reduction over about 120 hours. This is due to the non-sulfur dioxide content air inside our labs. Otherwise, my colleagues inside the labs will die after a few moments. Because this is a reason why we have those drastically decrease of the transient. If this takes place in 1969 in Dresden, the transient will not decrease. It will be half a steady state level, maybe at 80 or 60% for several hours. So that means we need to have a look to construction sites where it is possible that we will get moisture films inside of the ducts during the construction process, and where we will have high sulfur dioxide contents in the air. But afterwards, Gregor already showed it. What does a pre-stressing steel looks or surface looks? This is a surface which you will see when you replace those kinds of pre-stressing steel from the bridge structure, and you can't see any crack. You can't see any pits or holes due to corrosion processes, because the oxidation process from sulfurous to sulfuric acid is not a corrosion process. It's just an oxidation step, and this oxidation step forms hydrogen by themselves without any corrosion views on top of the mild scale of those kind of steels. But the same steel, due to the MT measurement, means magnetic powder measurement with fluorescence view, looks like that. There are several cracks inside, but it's impossible to see just by normal optical view. Yeah, how could this be possible? When we have a detailed look into our ducts at the inner side, due to the hydration process, we could have plus 40 to 60 degrees at the fresh concrete state, at the outside, +5 to -5 could be possible. And then we will get condensation water inside of the field between the pillars. It doesn't play such a big role because the moisture film is at the bottom of the duct and the pre-stressing steels in this range are on top. That's the reason why we couldn't find so many cracks in the middle of the structures. Directly above the pillar, it's completely different. The moisture film is formed on top, drops will form if the content is high enough, and those drops will fall down to the embedded pre-stressing steels. And afterwards, we will have the oxidation reaction from sulfurous to sulfuric acid, and this forms adsorbed hydrogen on top of our steels. And afterwards, if the stresses are high enough and the hydrogen amount is high enough, we will get cracks inside our high susceptible steels. And it's also able, we are also able to get an idea when we open those ducts for bridge instructions. It's also a picture Gregor showed you. We will have so-called corrosion products inside at the 12 o'clock position of the duct. From the outer side, you will see not a single corrosion product. If you open the duct and you will have a look to the top here, you will see corrosion products. And if you will see them, then it could be possible that you have exactly this reaction inside during the building process. And it also could be possible that you will have cracks inside the steel. So right now we definitely know the material is high susceptible, in this case of the Carolabrücke is Hennigsdorfer pre-stressing steel. Mechanical stresses are always given. And we have an idea about the electrolyte which was necessary for those drastically hydrogen evolution inside of the non-fulfilled ducts. Yeah, and there's something special. It's more or less a similar view like Gregor already showed. There's a so-called Tutti diagram. Normally, in case of a structure failure or during the service life, we have the initiation phase, maybe due to carbonation or chloride ingress, and we will have initiate a failure here, like pitting corrosion. The propagation phase, the corrosion pits are getting bigger and bigger. We have a cross-section loss, and several years later, the structure could collapse. In case of chloride ingress, could be a bit faster. In case of the normal kind of view, hydrogen-induced stress corrosion cracking could also accelerate the process. But the reality right now is something else. We never had an initiation phase. The construction starts to run under traffic with drastically damages at the pre-stressing steels because the cracks are always inside the steel before they will be fulfilled with mortar. And this is a completely different kind of view, especially for the problem of cracked wires regarding to fatigue. So Gregor already said it, it's not only a problem of the former German Democratic Republic, means Eastern Germany. We create a new measurement set up to check the susceptibility of pre-stressing steels in a time span of 24 hours. And here you can see the difference between high susceptible pre-stressing steels and the normal cold drawn one, which are already used in Italy. And this time span between 45 minutes until one of those Neptune wires could break, between 40 or 50 hours is quite big. And as you can see here, we have 4 different kinds of high susceptible steel products with the same strength class. This is Neptune. This is a former Western German product. The Hennigsdorfer pre-stressing steel, it's an Eastern German product. the sigma old and the new one. And as you can see here, the median of the breaking values, the Hennigsdorfer, where we currently saw the most critical bridge structures with high damages inside, is the robust one of the used, quenched and tempered pre-stressing steels in Germany. That means it's also possible, if we have a detailed look in structures with continuous girders directly above the pillar, opening the ducts, we will definitely find cracks at any kind of quenched and tempered steels if the doses of the sulfur dioxide inside the atmosphere was high enough to produce those kind of sulfurous acids. Now here you can see it. The robust one in place 4 is the Hennigsdorfer, and that's the one which was used to build the Carola bridge. In summary, the findings from the current damage case have prompted us to question parts of the previous approach to sampling pre-stressing steel bridges. Preferred damage area corresponds to the area with the highest applied moment. So it's directly above the pillar, it's clear. Previous sampling at moment 0 points are completely out of scope. You can't find any cracks in those areas under critical conditions. Also, if a high amount of sulfur dioxide is in the air. And also in the field, it's critically, you saw the results of the study from Gregor, where I think 93% of cracks would be found directly above the pillar in the highest point of the ducts. In addition, the sensitivity of tempered adhesion, means quench and tempered adhesion rods and wires with strength classes lower than 1,450 to 1,600 kPa or Newton per millimeter square must be checked. We already investigated the first ones with a lower strength class, and they are also high susceptible. That means the amount of bridges we have to check currently increased drastically. The susceptibility of pre-stressing steels in interaction with high concentrations of air pollutions leads to an exponentially higher degree of damage. That's the reason why we saw so many single cracks at one wire or multiple broken wires, which is a span of less than 10 centimeters between two completely cracks of the cross section. Thank you for your kind attention.
Thank you, Dr. Ebell. We will now go directly to the Q&A session. So we've got one question from the public, and I believe it is directed towards Dr. Schacht. So I'll read. According to your opinion, were the displacement mechanisms of the Carola bridge before the collapse? It can be assumed that there was certainly an increase in vertical deflection, but do you think that sector D, the tram section, could also have experienced horizontal displacement towards the east prior to the collapse? And if so, could this be related to the asymmetric loss of pre-stress? And finally, do you think that some parts of sector D may have moved upward before the collapse?
Okay, I start with the first question. Vertical displacements might have been there, but they must have been very small. So there was no, we didn't do a check 2 days ago, before 2 days before the collapse. So we never know how many cracks were really visible some days before. But the tram passed over the bridge, and the bridge stood clearly, and it took 8 minutes to fall down because of the cross girder I mentioned. You can see it in the back of Giovanni at the top of the tip of the cantilever. There was this cross section, and the superstructure laid on this cross girder, and only in the moment the last tendons or last wires broke at the support axis D, then the full weight of the cantilever arm laid on this cross girder, and then it fell down. So I don't know if there was many or much vertical displacement prior to the collapse, actually, yes. And the second question is that there's a, to explain the horizontal displacements, horizontal displacement to the east prior to the collapse. We also don't know that if there is if there has been horizontal displacements. We know from measurements from the hinges of the supported suspended girder that there were small deformations that went through an annual up and down moving. Yeah, so every year in the winter and in the summertime they had displacements that were repeatable, but there was I would say nothing that is connected to the collapse itself. Yeah. Okay.
Okay, thank you, Gregor. I have another question. If you could give us a preview of the monitoring measure recommended by the new German guideline. In particular, the monitoring system recommended are fiber optical sensor or strain gauge, and how it works, and if in the case of progressive collapse mechanism as the one observed in Carola Bridge, how they can help.
The mechanisms of the stress corrosion cracking, as we have maybe explained, Gino has said it a lot of times, it starts to crack at some day in the time of the use. Yes, the first wires break totally, and then they stepwise more and more wires are breaking. So this is a process. Not all wires break in one moment, so they break over the lifetime, and it's summing up and localizing, maybe or especially at the high points of the tendons. And for example, one method to detect these wire breaks is acoustic emission monitoring, which we use for a lot of bridges right now, and which will be yes, one way of monitoring written down in the guidelines. So this is one possibility to detect the active damage process, yes, because otherwise the deformations of the bridge will occur on a very late moment prior to the collapse, because many wires have to break before the prestressed concrete bridges deflect or have bigger vertical deflections or cracks, actually. A second thing is the fiber optical sensors. They can be used to also, first tests showed that it is working, to detect wire breaks with the fiber optical sensor itself, if it is close enough to the tendon. And on the other side, you detect cracking, beginning deformations with this measuring technique. And I think these two measuring techniques are the ones that are advised from the guideline. Yeah, strain gauges. I think you don't know where to place them actually, so it will be hard, or you have to place a lot of strain gauges to be able to get the same results you get with one fiber optical sensor, and that one is very cheap and you can install it easily. And yes, I think that's the better way of detecting. Yeah.
Thank you, very interesting. And then I have another question for Dr. Ebell. It's one interesting aspect that we have seen is the correlation between chemical corrosion and temperature gradients. Do you think, in your opinion, could this have an implication in future design of bridge, and in particular, if it could be a good point to give to create openings in a box girder in order to mitigate the temperature gradients?
So in general, due to the European standards we already have, those scenarios are does not taking place anymore. If we have longer time spans without fulfilling the ducts, it is necessary that we will heat up the volume of the ducts, or that we use inert gases to fill them up to avoid against any kind of corrosion. And at the other hand, if we will have a corrosion process due to a small moisture film, we don't have these amounts of sulfur dioxide inside the air more or less above whole Europe. So it's not possible to create those kind of scenarios right now or in the future. So it's not really necessary to observe temperature gradients or measuring moisture conditions or relative humidity inside of the ducts.
Thank you, Dr. Ebell. I will now pass over on to Nadia, who will lead.
Thanks. I have a last question for Dr. Schacht. If I correctly understood, the guidelines are useful also to address the structural investigation of the post-tensioned bridges. So my question is if they are based on international standards or not, and if they are available in English language.
I think they are not available in English. Yes, the guideline is not available. And the standards for the testing of these structures, I think it is specific for this kind of failure mechanisms. Yeah? So there are, of course, a lot of typical investigation methods which can be used for any structures. Yeah, but the specific rules or definitions, what is critical or not, are really focused on this stress corrosion cracking mechanisms. Yes.
Okay, but you have a similar instruction for other form of corrosion in German or not?
No.
Okay, so you don't have a general guidelines for post-tensioned bridges?
No, it's not a general one. Maybe we have a lot of problems with other kind of corrosion, especially chloride-induced pitting corrosion could be a problem in case of post-tension bridges. We also saw some damages of the ducts. They are completely corroded. The embedded pre-stressing steels having a lot of pits and cross-section loss. Also in case of quenched and tempered steels, they could lose the half of the cross-section or maybe 40% until they break, but they do not produce hydrogen-induced stress corrosion cracking due to chloride ingress or something like that.
Okay, thank you. I think we had an interesting discussion about these very hot topics also in Italy. And I think we have to thanking all our attendees for listening the presentation, the discussion. Then I would thank our moderators to have organized this webinar. And obviously, I would express our gratitude to our speakers, Dr. Schacht and Dr. Ebell, for their very interesting presentation. And I hope to see everyone next week for the second part of this webinar. Thanks you again to all.